I am Professor N.V.S.N. Sharma from NIT Warangal. I am here today to discuss on radar range equation. In the last class, we have seen what is a radar system, how does it help us to find any incoming object at a seaport or airport or at a battlefield without having any physical contact with it. So we came to know for this operation we need a transmitter, a receiver and an antenna system. So using these things, we know now that radar can be used to identify or to detect any incoming target, and also we can find the range, that is the distance at which the object is with reference to this radar system. So in this class we are going to develop an equation to find this distance in terms of the radar system parameters. Surprisingly, this is also dependent on the incoming target size, material and other parameters. So, taking all these into account, in this class we are going to derive an equation which is very much essential for any radar operator. At the same time, we are also going to understand on what basis we can avoid the detection of a target by a radar system. This equation helps us to understand and also to devise methods to escape the identification, or what we call it as to provide low observability. So we are learning two new parameters also. One is how is the object size affecting the radar system performance. We are going to discuss on radar range equation, or in short what is known as radar equation. In the last class we have seen how a radar can be used to identify or detect any incoming object or a target at an airport or a seaport or at a battlefield without having any physical contact. We also came to know about the way the range or the distance can be measured using a radar system. So in this class we are going to develop an equation in terms of the system parameters and also on the target parameters for the radar range. At the same time, we are also going to understand what is the design impact of this. Lastly, we are going to see how a radar can miss a particular target because of its inherent parameters, or what we call low observability. This will be highly useful in the military environment when you want the aircraft which you are sending to your enemy place not to be identified by the enemy radar systems. What you should do can be understood from this, the development of the radar range equation. Here in the slide you can see the equation directly first. Here R stands for the radar range, that is the distance of the target from the radar system, and it is given in terms of transmitter power, the gain of the transmitting antenna, the frequency of operation, the minimum signal required for the receiver, and also the target specific parameter called radar cross section, represented by the symbol sigma. The parameters mentioned are given in the slide now. So R is represented, take 2. R is given in terms of meters or kilometers in a normal case, but in military and maritime applications it will be mentioned in terms of nautical miles. The PT is the average power of the transmitter, normally in watts or kilowatts. The G is the gain of the antenna, it doesn't have any units. Then the lambda is the wavelength of operation, normally given in meters or centimeters. The sigma is the equivalent rectangular area of the target, and it is given in terms of meter square or square meters. Then Smin is the minimum detectable signal for the receiver. So it is also given in terms of milliwatts, microwatts, etc. The R is given in terms of all these parameters with a whole to the power of 1 by 4, that is 4th root of all these parameters beside the range. The whole radar operation is shown in the block diagram here. So just to recapitulate, this is given to you now, wherein we are first transmitting the signal through an antenna towards the incoming target. So as the waves propagate, they get expanded. So the power available at a particular point will get reduced. So at the location of the target, the power density is going to be very much less if the target is too far. Depending on the size of the target, it is going to receive certain amount of power on the surface. As the target is made up of metallic body, the power received will be again scattered. How much it is scattered depends on the conductivity of the material and also the shape of the target. So here the electrical parameter equivalent to this is given as the radar cross section, or the cross sectional area of the target as seen by the radar, and it is represented in meter square. So when the scattered power is again traveling, it gets reduced because it gets expanded. A very small portion of this is going to be present at the receiver location. Depending on the capability of the receiving antenna, we will have certain amount of power received. If this received power is greater than the minimum signal required for the receiver, then it will be properly processed within the receiver, and the indicator will be able to give a very good reading or accurate reading of the distance of the target, or what we call it as range. So here we are going to see that depending on the transmitter pulse width and the height, we can find out how much transmitter power on an average is being sent. Why we are saying on an average is, when the pulse is on, it is only for a short duration, most of the time in the cycle there is no power transmission. The radar will be waiting for the received signal. So average power is taken into account for this calculation. Power transmitted by an isotropic antenna. Just for hypothetical case we are considering here, then there will be a power density of Pt by 4 pi r square at a distance of r from the transmitting antenna location. This is very simple because an isotropic antenna radiates equally in all the directions. So power is equally distributed by this. So at the location of the target, which is at a distance of r, we take it that due to an isotropic transmitting antenna, the power density would have been Pt by 4 pi r square, watts per meter square. Then, in the present case, normally we go with a directional antenna. So, when the directional antenna is used, the power available at the target is going to be much higher. How much higher? It is by the gain of the directional antenna. So, due to the presence of a directional antenna, the power density available at the location of the target is going to be Pt into G by 4 pi r square. If this much power density is available at the location of the target is going to get certain amount of power. That is power density multiplied by area of the target. The area is what is seen by the radar system. That is the radar cross section of the target. So, the power present at the location of the target is going to be Pt into G by 4 pi r square multiplied by sigma, and the units will be watts. So depending on the sigma, you are going to have good amount of power available on the target. Now the target is going to scatter this in all the directions. We normally consider that the target acts like an isotropic antenna again. That is, it is going to radiate the signal in all the directions equally. So, the power scattered by the target is going to travel towards the transmitter again, and at the location of this radar system, the received power is going to be Pt into G by 4 pi r square multiplied by sigma divided by 4 pi r square will be the power density at the location of the receiver, and the units will be watts per meter square. Now we are going to take up the power available at the receiver location. So here receiver we mean all the systems are subsystems except the antenna, because we consider that antenna is a separate unit of the radar system. So the received power density multiplied by the antenna effective area will be considered for calculating the received power. So it comes out as Pt G sigma by 4 pi whole square r to the power 4 multiplied by effective area of the receiving antenna. Now we are going to substitute this in terms of the gain of the antenna, and putting this together we are going to find the total equation as Pt g square sigma lambda square by 4 pi whole cube r to the power 4 will be the received power at the receiving system. In the graph shown, you can see the relative power received proportional to the range of the target. So, as the target is very far off, the relative power E is going to be very small, and when the target comes close to the radar, the power received is going to be huge. So one has to take care of this very carefully, otherwise the receiver is likely to get saturated. So there are different ways and means by which we take precautionary measure of this variation. This good amount of variation is because of the dependence of the radar range and the receiver by fourth power. So a radar system is capable of detecting the targets as long as the received echo power is greater than or equal to minimum detectable signal of the receiver chain. If the minimum detectable signal is very less, it means that the radar can detect the targets which are very far off. If the minimum detectable signal is quite high, obviously very short distance targets can only be detected. So, if the radar range is decided first, we will try to identify a receiver which has a very low minimum detectable signal, or the sensitivity, which is normally expressed in dBm. A radar has to have a long range. That means if it has to detect targets which are hundreds of nautical miles away, then the transmitter power must be very high and the average power must be also quite large. That means the pulse amplitude must be quite high if the pulse width is going to be small. On the other hand, the receiver must be highly sensitive. That is, the minimum detectable signal must be very low, of the order of minus 110 dBm or even less. Whereas the transmitter powers will be of the order of 40 dBm W or 50 W, 60 dBW, etc. An increase in the transmitter power will have very small effect on the radar range. This is because the fourth power relationship between the transmitter power and the range. As you can see with an example on the slide, that by doubling the transmitter power, which is quite expensive, the improvement in the radar range is going to be only 19%. The average power can also be increased by increasing the pulse duty cycle or the width of the pulse, but in this context we are going to say this as time on target. That means you are going to transmit the power for longer time towards the target. A combined doubling of the pulse width and doubling of the transmitter power will give a fourfold increase in the average transmitted power. Even with this, the improvement in the radar range is going to be only about 41%. Then we will see what is the effect of the antenna gain. Antenna gain is a major parameter of interest in this because it comes into play in two instances. While the power is being transmitted, the antenna gain will try to concentrate most of this towards the target. Also, while the echo is coming to collect more amount of signal from the target, the gain helps us. So, improvement in gain of the antenna will have definitely a doubling effect. So, let us see for the case of a parabolic dish. For a parabolic dish, doubling the antenna size, that is, increasing the diameter of the parabola, will yield a fourfold increase in gain and accordingly a doubling of radar range. And this is a one-time effect. It is while you are thinking of an antenna for the radar system, find out the one which can be having highest gain possible. And with this, if you are operating a radar, you need not pay anything extra for the day-to-day activities. Like improvement in radar power of the transmitter, you need to spend more amount of money for that. But if you want to improve the gain, you need not spend much on that. So definitely the radar designer will try to see that the antenna that is being used will have highest amount of gain. That is why a parabolic dish is the popular choice. Similar to the effect of radar transmitter, the receiver also has similar effect on the radar range. That means if you reduce the receiver sensitivity by half, the improvement in the radar range is going to be only 19% again. But the complexity involved will be increasing drastically if you reduce the sensitivity to half. So, it is preferable to go for better antenna design than trying to increase the radar transmitter power or reduce the receiver sensitivity. So, simplistically, the smaller the radar pulse width, the larger the required receiver bandwidth and also the receiver noise floor. So, here you can see in slide 19 the requirement of receiver bandwidth. So, in time domain, when you are going to send a narrow pulse, it's going to occupy large bandwidth, and if you want to accommodate all the power that is available, the receiver must have wide bandwidth, hence more cost for that. If you can go for a broad pulse, then the spectrum of the pulse is going to be narrow and hence the receiver bandwidth requirement is also going to be less. But mind you, narrow the pulse, you will be able to identify even close by targets. If the pulse is very broad, then as long as the pulse is being transmitted, the receiver will be shut off and hence the close by targets cannot be detected. So this is the trade-off between the pulse width and the receiver bandwidth requirement. So here we understood already that the received signal must be definitely higher than the noise floor of the receiver. So in this diagram, you can see if the target is close by, the energy received will be very high and there will not be any ambiguity for the receiver between the signal and the noise. If the target is reasonably away, the received signal will also be less compared to earlier case and hence it will be slightly away or above from the noise floor of the receiver. Still, the receiver will not be making much of a mistake. But if the target is relatively very far, the received signal is going to be much less and just crosses the noise floor, and the receiver will be able to respond somewhat properly sometimes, not so good at other times. But if the target is much beyond this, definitely the received signal will be submerged in the noise and hence will not be detected. This gives us a clue regarding the unambiguous range determination of a radar system. That means at the third point of the graph, you can see the target can be detected properly. So that is the farthest point from which if the target sends any echo, it will be detected by the receiver. So that distance can be called as unambiguous range of the radar system. If the target is beyond this, then the radar will not be able to respond properly and the operator will not be able to decide the presence or absence of a target, or it may be not possible for the operator to decide anything about the targets. At the same time, there is another danger for us, that suppose noise crosses the signal level due to some unforeseen conditions. Then also there is a chance that the receiver responds to that and the operator may be alerted due to the presence of this. This is known as false alarm. That means without the presence of a target, still the operator gets an indication that a target is present. So there are two critical conditions we have. One is false alarm, the other one is missing the targets. So a proper choice must be made to see that the false alarm is minimal and the missing of the target is to be avoided. We are depicting these situations. At the receiver input, we are going to keep a threshold to decide whether the incoming signal is above the noise floor of the receiver or not. If the incoming signal crosses this threshold, then we conclude that there is a target present. If the signal is below this threshold, it will be ignored. So, how to decide this threshold is a very big question. It all depends on the location at which the radar is operating and the ability of the receiver to identify the incoming targets, etc. If you keep a low threshold, then due to the echo signals from the targets, definitely you are going to get a proper indication. But at times, the noise present may be crossing the low threshold limit and it may be indicated as though there is a target present to the operator. So physically there is no target present, but the indicator is giving you that there is a target. This condition is what we call as false alarm. This must be avoided at all situations. But if you want to avoid this, you may jump to the conclusion that you may put a high threshold level. But with a high threshold, you may be able to avoid false alarms or the noise itself crossing the threshold limits. But also, the far off targets will not be detected because the echo from these targets will be quite low compared to the threshold, and they will be ignored at the input itself. Hence, the selection of the threshold is a very intelligent choice. It should not be too low because we have to avoid false alarms. At the same time, it should not be too high to counter this missing of targets. This is a very crucial decision in the design of radar systems. In the initial portion of this lecture, I just gave an introduction about this. Let us try to see more aspects. Radar cross-section is not at all the cross-section view or something of the radar system. It is concerned with the target. In what way the target is presented to the radar, or from the radar point of view, how a target can be seen. That is, the equivalent rectangular area of the target as seen by the radar is represented by the term radar cross-section. So, as it represents cross-sectional area of the target, the units of this quantity will be meter square. And this radar cross-section depends on several parameters. It depends on the conductivity of the material used for the body of the target, the shape of the target, the look angle of the target from the radar, and several other parameters. You can see here a rectangular body with the size A for length and B for the width. If you take the RCS of this target, then you will get a very large RCS value because it's going to reflect good amount of signal. So its RCS value is going to be simply AB. Here you can see a sphere instead of a rectangle. Though the size of the sphere is quite large, the reflected signal towards the radar is going to be very small, and hence the RCS of this is going to be very less. So it all depends on the look angle of this. So the RCS of a sphere is given by simply pi r square. We are keeping a cylinder before the radar and trying to understand how much signal will be reflected by this, and hence what will be the RCS of this. So here the RCS can be small for certain look angles, it can be large for certain other look angles. The sigma or the RCS of the cylinder is going to be 2 pi r a square by lambda, and mind you, it is only in a particular look angle. With this, you can get an idea that more the RCS, the reflected signal is going to be more, and hence at the receiver you will have very little doubt about the presence of the target, and accordingly you can also make an accurate calculation of the range. On the other hand, if you want to avoid all this because you are sending the target towards your enemy radar system, then you can understand to have a low observability. How do we shape the target so that the RCS is very less? If the RCS is very less, the reflected signal from this target at the enemy radar is going to be small, and they will get confused that the target is quite far off. So by the time they get alerted, you are very close to the enemy location, and hence your target will be able to do the required harm to them very easily. So low observability is a military technique people try to employ. And for this low observability, we should see that the target is made up of low conducting material. Also, the shape is such a way that the scattered signal is much less towards the intercepting radar system. If you are able to do this with a large size target, then we call this as stealth operation. So stealth means how to avoid the observation of the enemy radar systems. So stealth is relatively new technology. The radome is at the nose, and which is large size, but it is made up of dielectric, so it doesn't reflect much. But the other parts like the gun muzzle, fuselage, leading edge of the tails, wing when viewed horizontally points, all these things will be the major sources of reflection of the incident electromagnetic energy, and thereby they give rise to high value of RCS. So if you want to avoid detection of your target by the enemy radars, you should see that the large reflecting areas are reduced drastically. You see that the metallic portions of the aircraft are reduced drastically, and this gives rise to low RCS. If low RCS is given, the performance of the radar system is also going to be very low. So if you want to have a good performance, the RCS of the target must be as high. So there is a trade-off between these two things. In this graph, you can see the RCS values of different day-to-day objects. So with the sizes of 0.301 meter square to 10,000 meter square, we have identified different objects like F-22 bombers, B-2, F-117, and birds, fighter aircrafts, bombers, ships, etc. On one side you have these F-22s giving very low RCS values. The human beings and birds, etc. will give reasonably good RCS, but the ships will be giving you very high RCS values of the order of 10,000 meter square. So with this, we are now in a position to understand what are the critical parameters to a radar system operation. One is the transmitter power, then the gain of the antenna, then the minimum received signal strength for the receiver. With all these three on hand, we will be able to identify or determine what is the maximum range unambiguously we can have for a particular system. Mind you, this also depends on the wavelength of operation. The one which we have used in this equation is only one type. And here we have considered that the receiver and the transmitter are at the same location. There are several variations possible into this. One primary thing is that here we have considered that it's a target like a bomber aircraft or a ship or a human being or a bird, wherein they will be like a point targets at a very large distance. There are occasions where we may have to handle distributed targets. For such cases, the same type of derivation can be done, and there the received power is going to be proportional to 1 by r square. Presently it is 1 by r to the power 4. So in distributed target's case, the received power is going to be definitely much large for the same range. The distributed target condition will be applicable where you are trying to send the signals into the atmosphere to understand the weather conditions. Similarly, from an aircraft, if you are trying to send the signals towards the ground to get an indication of the altitude of the aircraft and similar situations. So, this is one aspect. The other one is about the transmitter power. That is, more the average power, you can see definitely the improvement in the radar range, but it is not at par with the improvement required for the transmitter power. Similarly, the received signal strength should be higher than the minimum signal required for the receiver. If you can reduce this minimum signal requirement of the receiver even by half, we concluded that the improvement in the range could be maximum of 90%. So this is what we have derived in this class, and this is more or less on an idealistic assumption. There are several realistic things or parameters that are not included in this. So, with all these realistic values putting in, the actual range what you can get will be half of this theoretical value what we have derived just now. That means, if you take up the practical transmitter power, the practical received minimum signal strength required, the gain of the antenna, wavelength of operation and all other things, and calculate the range with this equation, that will be only theoretical range, and a thumb rule is that in practice you get only half of this value in your measurements. Let us do a simple example of this and try to understand much better for this. So, a specific air-sets radar has the following technical specifications. Its operating frequency is around 3 GHz. The peak power is 60 to 2200 kilowatts and PRF, and the gain of the antenna is 38.5 dB. And it is published that a maximum range of 250 miles for a nominal target can be obtained. If this is the case, you can calculate what is the receiver change sensitivity, and as I mentioned initially, it should be given in terms of dBm, dB over milliwatts. And these are the references for your topic on radar.
Question answer session refers to the topic of radar range equation. We shall have the questions first and then the answer from the
Yes.
So scattering depends on the material of the target. Which material offers less scattering?
scattering depends on material of the target. Which materials offer low scattering? That is, the scattering of the targets is due to the metallic nature of the objects. So, if the metallic nature is more, the scattering is going to be more from any target. Obviously, if the target is made up of dielectric materials or the electromagnetic wave absorbing materials like carbon, then the scattering is going to be less. These days, we are exploiting this technique for low scattering targets, though the target actual size is very high. Thus, the target is able to deceive the radar systems.
So does the minimum signal required depend on the amplifier's range of the receiver section?
Does minimum signal depends on the amplifier's range of receivers section? Yes. The minimum signal required for the receiver depends on what is the minimum signal the amplifier can amplify properly. That means if we have more number of amplifiers in the receiver, we can amplify a very low amplitude signal. Otherwise, we need a large amplitude input for the receiver to operate properly. So, the minimum signal required is directly proportional or directly related to the number of amplifiers present in the receiver system.
It is known that radar cross section depends on look angle. Objects flying very near to ground will have a very small look angle and thus low RCS. So how actually will these objects will be detected?
RCS depends on look angle. Objects flying near to ground will have very small look angle and thus low RCS. How will they be detected? It is not only low RCS but also a lot of noise because of ground noise that is going to enter when the antenna looks at these near ground targets. So, we shall look for alternative techniques to detect signals due to targets submerged in noise. One of them is to make use of Brewster angle method.
So, to increase the maximum range, we need to use a high peak power transmitter. Now, how do we obtain such a transmitter?
To increase the maximum range, we need high peak power transmitter. How is it obtained? Yes, to increase the maximum range, we need to transmit more amount of power as per the radar range equation. If we increase it by 16 times, the radar range can be increased only by a double. On the other hand, if the radar transmitter power falls by 4 times, then also we can detect the targets at double the distance. Sorry, take 2. If the radar transmitter power falls by 4 times, then also the range falls only by half. In this way, there is a direct relationship between the radar range possible and the transmitter power. So, in this, if you want to transmit more amount of power so that we can get more amount of range, the best alternative is to go for good amount of amplification of the signal after the modulation. And here we employ power amplifiers to amplify the signal to be transmitted. See, power amplifiers will give rise to good amount of efficiency of the order of 90% or so, but with a penalty on the distortion of the signal. But as the signal is going to be distorted in the atmosphere anyway, we allow certain amount of distortion in the signal at the advantage of getting higher amount of efficiency. Hence, we use class C or even class D amplifiers towards the end of the transmitter chain so that we will be able to transmit high peak power.
So, combination of horn and lens antenna is known to give a perfect plane wave. Why is it then parabolic antenna still so popular?
Combination of horn and lens antenna is known to give almost plane wave. Why is then we use parabolic dish? Horn antenna along with lens can give rise to a plane wave, but with low gain in the range of 15 to 20 dB only. This is sufficient for short range radars like police radar or muzzle velocity equipment, etc. But if you want have long range radar system which can detect the targets at hundreds of nautical miles or even farther, we need very high gain antennas like parabolic dish. In such a situation, we need to have the gain of the antenna to be definitely greater than 30 dB, which is possible with only parabolic dish. Hence, in most of the cases, we choose parabolic dish as a good option for the radar systems.
So reducing the radar pulse width causes the receiver bandwidth to increase. So how does this cause the receiver noise floor to increase, sir?
Reducing the pulse width causes the receiver bandwidth to increase. How does this cause the receiver noise floor to increase? Yes, here we are going to see the radar system operation from the basics. Here we have a pulse being transmitted during the transmitting time, and the receiver is on to see the echo from the target. So the receiver is open to receive any amount of signal, whether it is from target or from the atmosphere. So if the receiver bandwidth is high, it's going to attract good amount of noise from the atmosphere, or the noise floor is going to increase. The same thing is going to happen even if you reduce the pulse width or going for narrow pulses, because the off time is going to increase, which gives rise to more amount of noise in the receiver. Hence, the receiver noise floor is going to increase. To overcome this, we try to go with range gates. That means we are going to use several receivers in parallel. One receiver will be on for certain time duration of t1 seconds. The next one will be on for only t2 seconds. Third one is for t3 seconds, like this, so that the noise can enter into this receiver only for a short duration or around the expected time of the target. Hence, the noise floor is reduced at the expense of using multiple number of receivers.
Thank you.